Okay, this is section 4.2, video number 3. So everything that we've done in the previous videos has kind of led us up to this point. We have figured out how to find sums. We have figured out how to find the limit of those sums. And now we're actually going to use all of that to calculate the area. So we're going to need the following formulas. We're going to need to know that delta x, which is the change of your x values, is b minus a over n. If you really think about that, it makes sense. I'm taking the right-hand endpoint, subtracting the left-hand endpoint, so I'm taking the distance between the two endpoints, and I'm dividing it by the number of rectangles that I'm going to use, n rectangles. So that's going to be my base. It's going to be my change of x. We're also going to need to know that x sub I, which is basically the ith x value, I guess you would say, whatever x value it is we choose, would be gotten to if we take the starting point A and then we add I delta x's to it. So if I want to get to the 10th rectangle, I would start with A and then I would add 10 times delta x, and that would get me out to the 10th specific x rectangle. Okay, if that doesn't make any sense, you can always just memorize the formulas. Okay, so let's recall that the integral is the same thing as the limit of the sum. So the integral, that symbol, is the same as the limit of the sum. And then as you can see, the other part is pretty similar. The f of x dx and the f of x sub I delta x, it's really exactly the same thing. The dx just represents the infinitely small change of x's. F of x is the function. F of x sub I, again, is the function's height. Delta x is the base. They are really exactly the same. Okay, so let's use the limit definition of the integral to find the area of the region between the graph of the function, the x-axis, over the indicated interval. So we're going to have y equals 1 minus x squared, there's our function, that's our f of x, over the interval from -1 to 1. So according to this, let's go ahead and write it in the notation. We want to find the integral from a to b, -1 to 1, of f of x dx. The dx part is really important, so don't get lazy and leave that off. If you don't put dx, you're really not adding up anything of substance, because the dx is the base of the rectangles. You got to have the bases to multiply times the height to add up a bunch of rectangles. Okay, this is, according to our formula, the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I delta x. And that's coming right from that formula right there. So what do we need to find? We need to find delta x, and we need to find f of x sub I. So let's find those things. Delta x. Delta x is b minus a over n. b minus a over n. And we don't know what n is, so it stays n. But we can simplify the top. 1 minus minus 1 is 2. So delta x is 2 over n. I need x sub I. Well, according to our definition up here, x sub I is a. A value is -1. Oops. Plus, let's go back up here so we can see it, I times delta x. Well, that's just literally I times 2 over n. So we'll write it as 2 over n times I. Now I need f of, because that's what this part is, f of x sub I. Well, that means I'm going to take that whole x sub I and I'm going to plug it, all of this stuff right here gets plugged in to the x's in my f of x. So f of x sub I, as a matter of fact, let me erase this and make a little bit more room, because I might need a little more room to write it. F of x sub I is going to be 1 minus, I'm going to plug in -1 plus 2 over ni squared. That is f of x sub I. Okay, now I have everything I need to evaluate my limit of sums. So I'm going to take the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I, that's this, 1 minus negative 1 plus 2 over ni squared, delta x, but delta x is 2 over n. All right, let's simplify all this, and then we should be able to use our properties to figure out this limit. So we're going to take the limit as n goes to infinity. I goes from 1 to n in our sum. So this is going to be 1 minus, going to have to FOIL this. So negative 1 times negative 1 is 1. Negative 1 times 2ni is going to be negative 2ni, but if I double that, that's going to be negative 4 of them, so negative 4 over ni, plus the square of 2 over n times I, which is going to be 4 over n squared I squared. And then don't forget I've got this 2 over n, which I still have to multiply times the whole thing. I should have put that in a bracket right there. Okay, keep simplifying. Again, it gets a little tedious to write all this stuff out. It's not extremely difficult. There's a bunch of algebra, but it's not extremely difficult. So distributing the 1 minus into everything, so 1 minus 1 is 0. I have to distribute the minus sign into everything else. So what I should be left with is 4 over n times I minus 4 over n squared times I squared, still all times 2 over n. Okay, it's getting a little shorter now, so I can write stuff a little bit more horizontally here. So that's still going to be the limit of my sum. Distributing the 2 over n, we're going to get 8 over n squared I minus 8 over n cubed I squared. Okay, now I can use my properties. I can separate a bunch of stuff out. And after this problem, I'm probably going to start doing this in like one step so that I'm not writing so much. The first one, I'm going to separate out the 8 over n squared times my sum of I minus. Now I can separate out the 8 over n cubed times my sum of I squared. Okay, now we're going to take the limit as n goes to infinity. Now we're going to actually do some evaluating. So we're going to have 8 over n squared. The sum of I, remember, is n plus 1 over 2, minus 8 over n cubed. The sum of I squared is n plus 1, 2n plus 1 over 6. Technically, I guess I should put a bracket around that. Now, we don't have to combine anything if you realize that what you have is two different limits that we can evaluate. The first one, the numerator has a highest power of n squared if you were to distribute the n's together. So the leading coefficient of that is 8. The denominator, the leading coefficient of the n squared is 2. So I'm going to get 8 over 2, which is 4. Okay, the second limit, you have to be careful on this one. If I distribute the highest powered terms, I've got 3 things to distribute there. So I've got an n times n, which is n squared, times a 2n, which is 2n cubed. On the denominator, I have an n cubed. So the 2 is going to get multiplied by that 8, which is going to give me a 16 over the 6. So minus 16 over 6. Okay, 16 over 6 is 8/3. So if I want to combine those, I got to change 4 into terms of thirds, which is 12/3. Minus 8/3 there is going to be 4/3. So that is the integral that we found all the way from the beginning. So if I wanted to find the area between the curve and the x-axis from -1 to 1 of 1 minus x squared, the exact area is 4/3. Okay, again, these problems are not necessarily short, but they're not difficult. It's just they take a long time to get all the algebra and stuff done. Okay, another example. Using the limit definition of the integral to find the area of the region between the graph of the function and the x-axis over the indicated interval. So our function is 2x squared plus x cubed over the interval from 0 to 5. Okay, so we need to set up our integral. The integral goes from a to b, which is 0 to 5. Our integrand is 2x squared plus x cubed. That's our f of x. And don't forget the dx. That is the same thing as our limit as n goes to infinity of the sum of f of x of I delta x. So again, we need to find delta x, x of I, and f of x of I to be able to plug that stuff in. So delta x is b minus a over n. b minus a over n. So it's 5 over n. X of I. X of I is a, which in this case is 0. It's actually kind of nice, plus I times delta x. So that's 5 over n times I. So it's really just, because I don't need the plus 0, 5 over n times I. So f of x of I is what I get when I plug in the 5 over ni into the original equation. So it's 2, 5 over n, I squared, plus 5 over n times I cubed. That's f of x of I. Okay, let's go ahead and substitute all that stuff in now to our limit, and we should be able to evaluate. So the limit as n goes to infinity of the sum of f of x sub I. So I'm actually going to go ahead and simplify this. So the 5 over ni squared is going to give me 25 over n squared I squared. But then I have to multiply the 2. So I'm going to get 50 over n squared I squared, excuse me, plus, now I have to cube 5 over ni, so that's going to be 5 cubed, which is 125, over n cubed, I cubed. Okay, and that's what I'm taking the sum of. And then I have to multiply that still by delta x, which is 5 over n. Okay, so like I said, I'm going to start to shorten this process just a little bit. I'm going to distribute the 5 over n, but I'm also going to pull out the constants and separate the sums all at one time. So my next step is the limit as n goes to infinity. So let's see, distributing 5 times 50 is going to be 250. N times n squared on the bottom is going to give me n cubed. All that stuff can come out to the front. 250 over n cubed. That leaves me with the sum of I squared. So I'll simplify that in a second. 5 times 125 is going to be 625. The n cubed times the n in the denominator is n to the 4th. And that's going to leave me with the sum of I cubed. Okay, that's distributing everything and simplifying. So now let's go ahead and replace our information. So I have 250 over n cubed. I squared, we've done that one before. N plus 1, 2n plus 1 over 6. And then I cubed we really have not used before. That one is n squared, n plus 1 squared over 4. And now we're ready to evaluate our limit. Again, we don't need to simplify from here. We just need to realize what would happen if we did. So this does not really look like a 250, even though it is. That's better. Okay. So in the first limit, n cubed is the dominant term on the numerator and the denominator, so we need to look at the leading coefficients. It's going to be something over 6. Don't forget that 2 is part of the leading coefficient, so I multiply it by the 250 and we get 500. So 500 over 6. And then we're going to get, let's see, the dominating term in both of the numerator and the denominator are going to be n to the 4th, because if I squared this one, I would get an n squared as a leading term, times the n squared here would give me an n to the 4th, and all the leading coefficients there are 1, so it's 625 over 4. All right, let's reduce that stuff just a little bit here. Actually, no, let's not reduce it. Let's just change it all into 12ths, because even reducing it's not going to help. So change everything into 12ths. That means I multiply the first one by 2 over 2. So it's 1,000 over 12 plus, let's see, multiplying 625 times 3 is going to give us 1875, I believe. So we should get 2875 twelfths. And that would be, whatever that is the exact area. I don't think that reduces. I don't know the 3, see 10, 17, 20. No, 3 does not go into both of them. So that's it. That's reduced as much as possible.